Hello everyone. We are going to commence this month webinar conducted by Institute of Physics Sri Lanka. I am Shantha Gamage, President of IPSL. We have been organizing this webinar series to promote physics and its application, and also aware the public on hot key topics related to science. Before introducing our resource person today, I would like to warmly welcome all the participants of this webinar. Thank you for taking time out and being here today. So please mute your microphones and we will give you time at the end of the session to ask questions if you have any. Also, during this session, you can type your questions on the chat box so that I can ask your questions from the resource person. So today's webinar, we have invited very famous researcher and well-reputed person in the field of applied physics to give a presentation on modern applications of physics. Professor Mohemad Henini is the today's resource person, and he is the professor of applied physics, School of Physics and Astronomy, University of Nottingham. First of all, let me welcome Professor Henini on behalf of IPSL. We are honored by your presence. Thank you for accepting our invitation. Before formally begin the presentation, let me call upon Dr. Chathuri Nupiarachi, co-editor of IPSL and convener of the Committee of Popularizing of Physics, to introduce today's resource person. Thank you very much, and over to Dr. Chathuri.
Thank you so much, sir. I'm very honored and privileged to welcome our resource person today. Actually, Professor Mohemad Henini obtained his first degree at the University of Oran, Algeria. He went to Nottingham University and was awarded the PhD degree in 1984. And Professor Mohemad has over 25 years of experience in molecular beam epitaxy, which is MBE growth. And his particular specialty in the physics and technology of MBE growth for 3-5 electronic and optoelectronic devices. So also he has authored and quote 130 papers, and he is the founder of 2 international conferences, namely Low Dimensional Structures and Devices and Epitaxial Semiconductors on Pattern Substrates and Novel Index Surfaces. He has edited, ladies and gentlemen, over 6 books which were published by Elsevier and serves on the editorial board of several scientific journals. He's also the editor of Journal of Alloys and Compounds. So without wasting much time, it's my pleasure to invite Professor Mohemad Henini. Over to you, sir.
Well, good morning, everyone. Good morning, Professor Ganesh, and of course, Chathuri, for giving me the opportunity to talk to you today. So thank you so much indeed. And of course, this is a very unusual way to give lectures or seminars over the online, but I will try to do my best and I hope nothing can go wrong during this talk. Now, I am not sure, can I share my screen now to start? Let me see if I can share. I think I'm disabled, so somebody has to enable me to share my screen. I think my host has disabled me, but I need somebody to enable me to share my screen.
Yes, sir, you can share now. So,
okay. Oh, yes, now I can share it. Okay, let me just see, share screen. And let me just share. Okay. Can you see my my PowerPoint?
Yes, sir, we can see you.
Can you see it?
Yeah.
Okay. So thank you very much. So what I will try to do today actually is just to give you an overview about, what are the application of physics practically, and how, one has to go from research to industry to make these devices or these, practically applied physics. So this is general seminar, which is going to cover a bit of everything. So I am assuming, that nobody knows anything. So I'm trying to give something basic, and hopefully we can discuss this at the end if there's any question which are not clear. But let me start up with this first slide. Just, all start with this periodic table. As you can see, anything you do uses practically materials, and materials are made, some of them, of these atoms, or this from this periodic table. And of course, some are in very important materials, and the one I will be talking today, mainly, let me just see if I can point, mainly the one I'll be talking today are the group 3 for the Mendeleev table, the group 3 and the group 5. So like say gallium and arsenic, indium and arsenic, and so on. So it's the group 3 and the group 5. And of course, you're all aware of the group 4, which is silicon, which is a very, very famous material, semiconductor material. But all the time, it has been a challenge how to go from the basic research to the applied research. So this is really the bridge between basic research and applied research is a very, very tough and challenging matter. So this is what I'm trying to say to you, that, in order to go from the lab to the fab, that bridge is very, very important. Of course, you do very interesting research, but how are you going to apply it? And hopefully today, I will show you a lot of examples how actually, all the things we do in the lab can be applied in the real devices, in the real world. So this is actually the outline of my talk. So let me just see my talk. So practically, I will start with the general introduction, but I'm going to start as far as in the late 1800s with Thomas Edison. And you will know why. You see, all this research being done hundreds of years ago. As people say, we have to stand on the shoulder of giants. So people have done already some work until now. And one thing I will discuss is how this transistor discovery, which may change actually our world completely. But I will try to, as well, to show you how, when we make these devices or these structures smaller and smaller, how, for example, the classical mechanics is not anymore valid, and that's what we have to talk about, quantum mechanics or quantum system. And I will show you some quantum devices, of course, during my lecture. And this is what we call them low dimensional structure. These are structures of the order of few nanometers. But one of these structures is which we call semiconductor heterostructure, which are made actually from different material systems. I'll show you some from the group 3 and the group 5. That what I call the God-made or man-made crystals, because these are perfect crystals, but it's not, you don't find in nature, but you have to make them yourself. And I will conclude. I start with Thomas Edison, and I will finish by Thomas Edison and what he calls a genius in research. So first, let me show you how applied physics in everyday experience. So as you know, the technology is part of our everyday life. And we all use computers like the one I'm using today. We all use smartphone, as you know, and many, many devices we use today. This is the evidence how practically applied physics. And all these devices, there is some physics in them, and that's most of them actually is quantum physics in them. So therefore, these technological advances are the end result of scientific discoveries or basic research. All started in the lab and all finished applied in the commercial world. So basic research is extremely important to make these devices. But again, not every basic research will end up with the real device, unfortunately. So here just practically to show you this diagram. All starts practically from the basic research, all right? And you practically, you make some development before you go to commercial products. And for these, practically for the basic research, you need government funding. So without the government funding, it's very hard to do the basic basic research. So as you can see, times are becoming challenging, especially during this COVID situation, to find the funding to do the basic research. And of course, if you want to commercialize this the research you have done in your lab, now you need a different kind of funding, and this is what we call the corporate funding. And this is extremely important, because the people who are going to help you to commercialize your products, they want to make money, and they want to invest something which is going to be really applied. So as you can see, the funding, whether the government or corporate agencies, is extremely important, to develop this basic research, which I would say from basic to applied commercial applications. So let me start what I call a great story in the laboratory in 1883, in the late 1800s, by Thomas Edison. So what he see that when he heat a filament, he see a current flow in a nearby electrode. So all he does, he heat a filament. What he sees a current, and this flow of current, what we call now electrons, is from metal, and is caused by heating. And then the heating, what is caused some vibration in the metal, and that's help you to get some charges or some particles. Those days we didn't know what those particles were, but we just called them flow of charges. And this is what is called the thermoionic emission, which means just you heat a filament, and then that filament, when it's hot, it's practically, it passes, it emits some charges. So it started, as you can see, many years ago, over 100 years ago. So this is how it's been. Thomas Edison, as you know, he's the inventor of the light bulb, which is the light bulb is only just a wire inside, heat it up, and you get electrons out of it. So another guy who took this idea, John Ambrose, and what he created what we call the vacuum tube only a few years ago, maybe nearly 10 years later. So that's what he called the vacuum tube. That's the vacuum tube, but that's what we call today the diode, the semiconductor diode. It has got the same application, but of course the size of the vacuum tube and the size of this semiconductor diodes today are very different, and I'll show you some example. Again, what he does, he just heat a filament, and that filament practically emit electrons, and you got a plate here, what we call the anode those days, and then you can control the flow of these charges, which goes from the anode to the cathode. And this is what, and depending how you bias it, you can have a flow of discharge in one way, but not in the other way. So this is, as you can see, in this case, electron flow only from the filament to the plate, depending on the voltage you apply. So this is actually, as you can see, starting from Edison and then going to this tube, which becomes a diode. And of course, J.J. Thomson, he used this tube. Actually, what he sees when he used this tube, he was very clever. He used this filament, but what he saw, that these charges, or this charge, we didn't know what they were, are deflected by magnetic field, and they are also deflected by electric field. So here, for example, you generate, you heat your filament, you generate some charges, and you apply either magnetic field or electric field, practically, and then you can deflect these charges. So practically his experiment, which showed that there are some negative charges coming from this heated filament. As you can see, the heat filament coming through here. It can be deflected by a voltage or a magnetic field. This is what we call nowadays now the Lorentz force, on particle charge. And this is what led to his Nobel Prize for Thomson, for discovering this negative charge. And of course, going from there, this Lee de Forest, he practically invented what we call the triode. And these are, again, they are vacuum tubes. And this time, actually, these triodes are practically 3 terminals. So what we call the cathode and the anode, and this is the grid. Okay, so in nowadays, this vacuum tube is a transistor, which I will show you later on, is semiconductor transistor, and the grid actually is called the gate. We still have an emitter now. We call them emitter, and the grid, and this is different kind of device, much smaller, of course, than this triode. So, but what he found that this triode device practically acts as an amplifier. It amplifies signal, electrical signal. So you can see how we went from the simple filament to a diode, and now actually a triode, a vacuum tube. These are very, very big, which use filaments. So this is the beginning, what we say, of electronics or microelectronics. And why? Because the negative charges becomes called electrons, and that's where the word electronics or microelectrons comes from, because of this negative charge were called electrons, and they carry a negative charge. And these are actually the tube, the vacuum tube. As you can see, this, you can hold them in your hand. These are very, very big. These are, for example, triodes, which are being used as amplifier. Unfortunately, probably you were too young to have a TV which had this kind of triode. But these have been discontinued many, many years ago, because these are not really, these are single device, one triode, one single device, very, very large and very, very consume a lot of power, and they die very, very, very quickly. But you see the size of these devices. So this is the first electronics computer using this valve practically, and you can see this practically, see how space this occupy, this first electron computer. But look at the speed, 5,000 addition per second. Its memory 200 digits. Now we talk about hundreds of tera digits. Look at the vacuum tubes, 18,000 tubes. Look at the weight, 30,000 kilos, and they occupy 180 square meters. So you see how big these things were and how unreliable these things were. And, but this how it all started, from this, again, this filament which produce electrons, how we made the triode, and how this triode has been used to first make the first computer. So now let's jump a lot in time. This in the mid 1900s. This is the birth of what you call the transistors or the triode. So this is the guys from Bell Labs who've been using, for example, germanium, which is group 4. And this is, that's what they call the point contact transistors. But look now, even these transistors, what you call now, what we call, the anode and the cathode are called emitter and collector. And of course, what you call now the base or the gate, if you wish to, for this transistor. But again, you can see this is very, very large device, but now it uses a material which is germanium, but it's much, much smaller than the triode. So this is the first transistors, the birth of the transistors at Bell Labs in USA. And this was followed by the transistor. Okay, so now we can make these transistors again, become the key device for this amplifier, for example, which consists for an emitter and the base, which control the flow of current from the emitter to the collector. But again, if you look at these, they are very, very crude kind of first junction transistors, you say, but this is the first, I would say, the birth of a new device made of a semiconductor. But now, I would like to jump because there is a lot of things that has happened in between, but I don't want to go through the whole history. But this transistors, the first application was in Japan. And this was the first transistor radio, which was built by Sony for practically the mass production in the mid-50s, 1954 practically. So this is the first application of the transistor, but you can see here, it took about 10 years, 1947 to about 1954, to make this device really small to fit in this kind of transistor radio. So the Japanese were mainly interested in consumer application, but in the US, the transistors were mainly used for computers and military applications. So there were two different paths. For Japanese want for more, consumer. The US want more for computers and military applications. And of course, we know this Shockley, Bardeen, and Bratton, they got the Nobel Prize for the invention of the transistor. This is the junction transistor for this, and they got the Nobel Prize about 10 years, few years later after the discovery. So that was a single transistor because all these applications had a single transistor. It's like the triad. Now it comes to the age of the integrated circuit. So this is probably all familiar with Jack Kilby from Texas Instruments, who invented the first integrated circuit. But I just would like to draw your attention, this is what it looked like. This integrated circuit means you're gonna integrate many devices in one chip. So this was a good chip, for example, and they have only probably one transistor, one resistance, and probably one capacitor. So it was very, very crude integrated circuit. And of course, he received his Nobel Prize, in 2000. As you can see, it's about 40 years later for the invention of the integrated circuit, mainly for communication technology. But look, I'm going to jump many, many years ago. So this is practically an integrated circuit which was developed by Jack Kilby in 1958. We had only few components, and this is practically the chip people use nowadays in the fabs, semiconductor fabs. And you can see now, this gentleman is holding a wafer which has basically a single chip in here, has got millions of transistors. So this is practically the heart of the modern computers, or if you wish, all these laptops have this modern integrated circuit who have got millions and millions of transistors in a fingerprint, in your finger, at the tip of your finger. So you can see how the technology from something very, very large to very, very, very small. As I can see, as I said, transistors within a single chip. I don't just want to jump now all these inventions. As you can see, the first transistors in the late 40s, the first transistors application, it took about nearly 10 years, 7 years. First calculators, first microprocessors. As you can see, this takes time really to make these devices applied. But of course, in early, practically 2000, this was the first Pentium, which had about 10 million transistors. So this again, Jack Kilby, who got his Nobel Prize in 2000, because now we went from these single transistors, very, very crude, to a very crude integrated circuit, to a Pentium 3, which has got 10 millions of transistors in single chip. And you can see how we went from something very, very big to something very, 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 very small. And this just again shows you, going from this triad, of course, going to the transistor and going to this integrated circuit. As you can see, this integrated circuit, as I said, it contains millions of these transistors in a single chip. Okay, so you can see the scale of the modern application of this circuit. So here was quantum physics come into play. When you start making things smaller and smaller, of course, when you're integrating, for example, hundreds of millions of transistors in a single chip, that means they're going to be smaller and smaller, which means they're going to be closer and closer. And of course, the quantum, the classical mechanics, which practically is just looking at particles, it's not anymore valid. And this is the question you have to think about this charge, the electrons. Is it a particle or is it a wave? And that's the question. And for people who design these devices on such a small scale here I mean in the order of nanometers, devices of the order of nanometer scale, therefore they need to understand the quantum mechanical effects in these devices. So all the devices I'll be discussing today are mainly quantum devices, which rely on a quantum mechanical effect. And I'm not gonna practically use all of them today. I'm just gonna pick up some few just to illustrate how quantum physics is important for these modern devices. So why we need quantum mechanics again? Because of course, as Moore's law, it takes us to this modern electronics, into the regime where quantum mechanics is important, because the number of devices has been increasing with time in an integrated circuit, as we went from just few hundreds to really millions. And therefore, we are in this regime. And Gordon Moore is, of course, the founder of Intel. He predicted that now we're going, he predicted that practically the integration is about, it will double every practically 18 months. You double the number of transistors in a chip about 18 months. And this has actually been increasing with time. Every 18 months it's been increasing. But of course, you will reach a regime where you cannot really make things smaller, anymore smaller, because the smallest you can make is an atom. And that's become very challenging. But nowadays, the transistors we make, this gate, or this, if you wish, the grid in that triad I discussed about, or this gate or the base, is about 10 nanometers in scale. And as you can see, in 10 nanometers already in the quantum regime, practically. And we're not anymore talking about a device which practically carry, hundreds of electrons, but we're talking about devices which are practically using very few electrons. So therefore, the design of these devices really require engineers to the quantum mechanical effects in these devices to make something new and exciting. And the semiconductors heterostructures, which is practically make all these devices I'm going to discuss, they are a new kind of semiconductor material. They're called heterostructures. And all the devices you can think of, all modern devices, are made of heterostructure. Heterostructure means you're practically stacking materials of different kind of materials, one on top of the other. And then you make something different, new. And I will show you how we make this heterostructure. But all the devices you can think of, whether transistors, lasers, light-emitting diodes, solar cells, whatever you can think, practically they are made of these heterostructures. And it's what is practically, it's a revolution in semiconductor industry of the 21st century, because everything we use nowadays contain transistors, lasers, light-emitting diodes, and I will show you many examples where they are used, and they all use some quantum mechanical effect, because we will be allowed to control both the electrons and the holes, the energies, which allows us to change their properties. Again, this new kind of semiconductor materials, or heterostructures, have been practically used by Alferov and Chroma, one Russian and one in the US, to make what we call semiconductor heterostructure for high speed and optoelectronics. Mainly they actually started with lasers. So they were the first actually who proposed ideas to build semiconductor lasers from these heterostructure devices. And that was actually, as you can see, it's only about 40, 50 years ago, since this idea came of using these heterostructures. So they are very important kind of structures in quantum mechanics. And this is just what I picked up from Yasashi, who put this very nice actually diagram showing what we call the heterostructure tree. So you can see any device you can think of is within this tree, whether it's solar cells, gallium arsenide integrated circuit, light emitting diode, PIN diode, laser diode, you can think whatever you can think is in this tree. And all these devices will practically rely on a substrate where you're going to make, because all these devices rely on some thin films. You need practically a template, what we call the substrate, to make this thin film. You need to deposit this thin film by using different technique. You need, of course, some fabrication technology to make the devices. And of course, you need to characterize this material and see how they behave. So as you can see, this is really amazing number of applications from these heterostructures. So how are we going to make these heterostructures? Here is what I'm going to show you. And again, I'm going to only concentrate on the group 3 and the group 5, but you can make it from the group 2 and the group 6. You can make it from the group 4. All the devices I'm going to discuss are practically from semiconductors, which are between metals and insulators. And this I'm going to show you how we can make or create these heterostructures by using these epitaxial growth techniques, which means you just deposit these films layer per layer. I just picked up here, for example, aluminum from the group 3, arsenic from the group 5, gallium from the group 3, and so on. So, as I said before, you need a substrate, And the substrate usually is about 400 micron thick. This is actually the template where you put your thin films, and all these layers here are only a few angstrom or few nanometers thick. So these are very thin films. And you can deposit this by what we call molecular beam epitaxy, or what we call metal organic chemical vapor deposit, MOCVD. There are two different techniques, major techniques, but there are many variants to make these structures. So I don't want to go to the details because all those techniques actually, it's a lecture in themselves, but this is just how we can deposit, for example, molecular beam epitaxy. We can just deposit layer per layer of aluminum, layer of arsenic, layer of gallium, layer of arsenic, and so on. And you build it as a sandwich structure. And that sandwich structures, depend what you want to create, what kind of device you want to make. And I will show you some few examples. But when you stack these materials one on top of the other, what are you changing? So here is just, again, I use aluminum gallium arsenide because you can have any sandwich structure you wish to. You can dream of what you want to what kind of material. Here, what you see, one thing when you stack this material on top of the other is the energy as a function of Z, energy of electrons if you wish to. So, and I'm gonna jump to the notion of the energy bond gap. So if you take the energy bond gap of aluminum gallium arsenide, is very large. So this is actually the conduction bond and the valence bond of this material system, and this is the gap. So that means there is no electrons or holes in this energy region. Only they are in the conduction bond on the valence bond. This is the forbidden region, energy region, which we call the bond gap. So it has got a large bond gap. The gallium arsenide actually has a lower energy gap. And then if you top it up with aluminum gallium arsenide, it has got a larger energy gap. So what you have formed here, energetically, a quantum well. So this is what you call a barrier, and this is a quantum well. And what you have introduced in this quantum well, energy state, both in the conduction bond and the valence bond, which means now the charges, electrons, for example, can only occupy certain energy state in this quantum well, both in the conduction bond and in the valence bond. So this is what start having quantized state inside this energy state. So you will see, from the next slide, how this is important. So by creating these quantum wells, both in the conduction bond, these quantum wells for electrons and for holes, what we have created some quantization of both electrons and holes. That means they will have specific energies which we can determine. And these energies practically depend, for example, on the width of this quantum well. If the width of the quantum well is very, very large, this energy is very, very small. If it's this width is very narrow, this energy state is very, very high. So actually you can control the energy of these electrons by just changing the width of the quantum well. So this one, I'm going to show you the size quantization in heterostructures. I will start with the bulk. This diagram and this diagram is exactly the same. This diagram and this diagram just show to highlight the differences between them in a second. So here, what we call a bulk of 3D materials. A bulk of 3D materials means these sizes are very large. X, Y, Z are very large, which means that the electrons or holes are free to move in all 3 dimensions. However, if you reduce this dimension to this size, for example, in this Y direction, we reduce this direction, but so this is what we call a quantum well, which means we reduce the freedom of the electron only to 2 dimensions. So now practically the electron can only move along the plane. It's practically quantized along this direction, Ly, okay? If we make this now even smaller and smaller, so we can practically make this Lx smaller, Ly smaller, but this is long wire. So now we can see the electrons only have got 1 dimension of freedom. It's along this direction. I will say Lz. Or can make a box. So where all these Ly, Lx, Lz are very, very small. And this is what we call a quantum box or quantum dot. But when you reduce this bulk, the dimension of this bulk from this to this quantum box, what you have changed, something very important in quantum physics, you have changed the density of state. That's the number of energy states which are available to the charge, either electrons or holes. So you can see for a 3D bulk, it's really continuous. For a quantum dot or quantum box, it's a delta function. That means you got a lot of energy states which the electron can occupy. So if you think about any device, whether it's a laser diode, whether it's a light emitting diode, whether it's solar cells, it consists of a p-n junction. P means you got a positive charge, N means negative charge, and it's a p-n junction. All right. So all these devices I'm going to talk are made of a p-n junction, and it can be what you call a double heterostructure, where this white region is very large. This is what we call 3D, for example, bulk material, because this could be 1 micron. But I can reduce this region here, this white region, to a few nanometers and becomes quantum well, or can make wires, or I can make boxes. But here you can see again the density of state of these electrons and holes. But let's just talk about the electrons. You can see this is continuous, but at a low energy, we only have a very small density of state at this point here. But when you go for quantum dots, at the lowest energy, we got a huge energy density of state. What does it mean? If we want to make a laser, we want to have a very high density of state, which means we want a very large number of electrons and holes to recombine to give us a photon. So if you use this device, we call double heterostructure or quantum dot laser, we expect this quantum laser to be really much better than this or the quantum one, because we got a large number of energy density of states, which means we're going to have a large number of charges, electrons, and holes, which are going to recombine, which means that's going to have a lot of photons, which means it's going to have high gain. And this is what really started all this, what you call low dimensional structures and devices. But of course, there was no technique to really make this kind of nanometer scale thicknesses in the time. So this is what really started all this research on heterostructures. This was the first patent in 1976 from Bell Labs, who used this notion of density of state when you reduce the dimension of the system from 3D bulk, 2D quantum wire, 1D wire. At those days, they didn't even think of quantum boxes or quantum dots. And what they predicted, if you can make devices which are based on this dimension 1D, 2D, then you can really use this quantum effect to make some really semiconductor lasers. But in 1976, there was no technique which can make these thin films. And this was started actually people thinking how we're going to create this technique to make these thin films. And this is how molecular beam epitaxy and MOCVD came to light in the early 80s. It didn't take too much time. And it was a race to make these quantum devices by these two techniques. But just to show you here, the advantage of using thin films in terms of lasers, in terms of semiconductor lasers. So here's what I'm plotting here: the threshold current and time for different kind of structures. The threshold current of a laser, as you will know, in order for this laser to laze, this structure to laze, you need to pass a certain current. It means that you need to inject electrons and holes before they recombine and give you a photon. And you want that threshold current to be as small as possible. This is a figure of merit for the laser. If this current is too high, that means it will burn very, very quickly, and the lifetime will be very, very short. But look, in the early 60s, most of the lasers used these three-dimensional devices, which we call a double heterostructure, and the current density was really high, 1,000 amp per square centimeters. In the early 80s, when this MBE came to life and the MOCVD people started making quantum wave lasers, but within a very short time, the threshold current becomes really small, around 20 to 30 amps per square centimeters, really small. And then when we started making quantum dots in the mid-90s, this current practically dropped to really around 10 milliamp, 10, 15 milliamp per square centimeters. As you can see now, by reducing the dimension of the system, using this quantization effect, we managed actually to reduce the threshold current to really small devices. And now these lasers have, 1,000 hours lifetime compared to maybe very, very few hours for these double heterostructured lasers. Now let me just go to a new quantum device, and of course, all those was due to the quantization. I don't want to go into much details using these quantum wells, and of course, as I said, these lasers, you can have different wavelengths of lasers by using different kind of material system, different confinement system. You can practically tune the wavelength by using different materials and different structures to go from infrared to the visible to UV light as well. So you can cover all these devices by using these p-n junction lasers. So lasers really rely on an electrons and the hole to recombine to give you a photon. However, there is a new breed of lasers, which we call quantum cascade lasers. So remember, now we're using this word quantum because it's all quantum phenomena. And this cascade is very important lasers. So these lasers actually, again, been practically invented in Bell Labs. But these lasers, they don't work in the visible. They work practically from the mid to far infrared, you see. So you can see here, the kind of lasers we want, depending on the we want shorter wavelength for the visible, we want the longer wavelength for the infrared, for different application. But just I want to pick up these quantum lasers because it's a very different than the normal laser. So a normal laser, it relies as for an electrons and the hole, an electron in the conduction bond and the hole in the valence bond to recombine to give you a photon. In the quantum cascade laser, you don't need holes. You just need electrons. So what you devise, this device a quantum well, as you can see a quantum well, and you can have different energy states depending on the size of the quantum well. And all you look at now are some transition from this state 2, for example, to state 1, and then this will give you a photon. But the energy of this photon is much, much smaller than the energy of this photon. That means smaller energy, that means a longer wavelength. So this device only rely on electrons, not on holes. So this is only transition, or that's what we call inter-subband transition. And inter-subband, depending which one you want. So here is for this interband, going from this band to this band, this inter-subband. So all these are subband within the quantum well. And this is the difference between the two again, because here you got only one energy state, for example, one in the conduction bond, one in the valence bond. But in the quantum cascade laser, you got two energy states, both in the conduction bond of the system. And you can see the energy is much, much smaller. And this practically quantum cascade because you need a lot of quantum wells. So this just show you multi-quantum wells having certain number of energy states, at least two energy states. And this one you apply a bias because all time you need, of course, to apply a bias to push this electron through the system. So it's your multi-quantum one. And all these sizes are practically few angstrom sizes. The barrier and the quantum one are very, very thin layers. And this is how it works. So you inject, for example, when you apply a bias, you inject an electron to this energy state, it practically relaxes to the low energy states, emits a photon, and then what's happened, the other electrons tunnel practically, it tunnel to the highest energy states, fall down, emit a photon, and you can see. So you can see we got some new phenomenon which I don't go through today, what we call electron tunneling, and we got here this subband transition, which allow you to send a photon, as you can see here. And this actually structure is very, very complex. You say, just showing transmission electron microscopy of this structure, and you can see all these are very, very thin layers. And you can see here how we use this system for tunneling and this system here, the quantum one, practically to have this energy state. This transition, and of course, the energy of this transition depends on the size of this quantum well. And why we call it quantum cascade, because it's like water, it cascades. The electron come here, can go down, go through this layer, come down, and so on. It's like a waterfall, it cascades down the energy state. You see, that's what we call it a photon. So, but you can see electron jump from one energy state level to another and tunnel from one layer to the next. It's another quantum phenomenon, tunneling as well. So as you can see here, the wavelength we emit depends only on the heterostructure geometry, not on the material properties. You can use any material. It's actually about the heterostructure, about the quantum well of the size of that quantum well, which determines the wavelength. It's not based on a p-n diode, and only one electron is needed to produce multiphoton. But you can see here, one electron allows you to produce a multiphoton. For previously, you need one photon per electrons, you see. But here, you see, that's what you got. This only one electron is needed to produce multiple photon. Now, just to demonstrate to these lasers, because lasers is very important. Those are very important. So those all were in the lab, but of course, you have to commercialize them. And you need some kind of machine. All those devices I discussed earlier are using what we call research MBE machine, molecular beam epitaxy machine. But of course, you want to scale things up and you must produce them. You need what we call production MBE system. And these are very large MBE system. And I will show you their capacity, in order to make them very, very useful for mass production. There are not many companies who make this MBE system. There are about 2-3 companies in the world who make this system. One in France, one in USA, there's some in Japan. These are the major companies which make this machine. So here, there's a long range of end-use markets. But all the time, you have to start with this epitaxial machine. You need the wafers, because this is a template where you're going to deposit the thin films. You need to fabricate the devices, and of course, you need to. These are the application. All this heterostructure discussed with before. They use in many transistors are used in wireless telephoning. Many in local area networks. Satellite, I will show you, for example, in some satellite there are transistors, but there are solar cells as well. Audio and video, lasers, for example, blue lasers, red lasers, they're all using heterostructures for these CD players. In healthcare, there are many different devices, including lasers, for example. In cars, light emitting diodes, collision avoidance system, all are based on some heterostructures of one way or another. So there's a huge number of applications. I'll just practically show you, some application of heterostructure, especially the transistor. So these are transistors called high electron mobility transistors. It's called HEMT, high electron mobility transistors. In your mobile phone, you got at least one transistors. All these smartphones made of gallium arsenide. It is heterostructure, and it's a very high speed, high frequency transistor, which is in these mobile devices. Okay, so this is, as you can see, there are a lot of applications of these new transistors. The transistors I discussed earlier before, you see the silicon are much slower than these new devices made of 3.5. They have got very large mobility, which means high frequency, and they are used in this kind of, and that is, of course, a high amplification too. Laser diodes. So here I'll just actually give you one example of these transistors, because the mobile phone has become really a part of our life, and that's how we need this mass production MB system to make this kind of transistors. Unfortunately, my time is limited to discuss this kind of transistors, but to show you there are transistors. Laser diodes, I don't need to tell you what they're used. If you just think about your laser printer, so that laser printer, which we use now every day, is based on laser diode. It's a heterostructure. It's a heterostructure and a semiconductor based on quantum phenomena. But you can get them, of course, in communication. Laser. All the lasers we use in optical, all the devices we use in optical fiber telecommunication use a laser diode operating at either 1.3 micron or 1.55 micron. So there are many applications of laser diodes, both, as I can say, for something we do every day, to something we're not aware of, like, telecommunication. And actually, about 60% of all the laser diodes are used in telecommunications. But of course, There's of course the consumer application, especially these CD players and so on. And of course, I don't need to tell you about lasers, because if you think about the two major things which changed our life are the transistors and the lasers. They are used everywhere. Lasers and transistors are the two biggest invention in our history. As I said, telecommunication along optical fibers, they use lasers. Consumer application, you see them every day in your CD players. These quantum cascade lasers are mainly used practically in detection of gases because they use a long wavelength. There are many different other kind of different lasers. All the lasers I've been discussing with you are what you call edge emitting lasers. They emit at the edge of the device, but that's what we call vertical cavity surface emitting laser, where the laser is emitting at the surface, and they got different application, of course. And of course, there are many applications in medicine, for the skin, for the eye surgery, who use lasers. And of course, law enforcement, as I said, for speed and distance of vehicles, that's what they use. There's actually practically, a tuning device, which is very, very fast, operating at high frequency. So all these devices are very, very, all these heteroaction are used in many, many applications, which probably we're not aware of. And they all use a quantum phenomena or quantum device. Let me again touch on something which is very important again, is this heterostructure solar cells. Again, as you can see now, it's not only lasers and of course transistors, which are very advanced, but now we are in different times. We need to think about clean energy, and solar cells are some of the topic which are very, very hot topic. How we can generate electricity without practically damaging our Earth. And this is what the solar cells. And solar cells, as I said, it's the same kind of device. It's a p-n junction, same as the laser, practically. But just look at the first solar cell, which was used in a satellite in the late 50s. As you can see, this was made of silicon. It was only about centimeter by centimeter. And see how the technology has practically changed our life. Now, for example, I'm just showing you practically, a panel for these labs in space, which, as you can see, they are huge solar panels. So just to give you the scale of these two gentlemen and the size of this panel. So you can see how now we have practically using this solar energy, for example, in space. These are different kinds of solar cells. And the race is how to produce actually high efficiency solar cells. This is very, very important. And that's what they are different materials, what they're using silicon for a terrestrial application, or using the 3-5 semiconductor for space application. But all those are based on heterostructures made from the group 3 and the group 5 or the group 4 as well. And just to give you some, some ideas about the solar panel in for example, in this space station, all using heterostructures. So to come to my conclusion, I start with Thomas Edison, and I finish with Thomas Edison. And he said, he did ask himself, what is a genius? And this answer was, a genius is 1% inspiration and 99% perspiration. That means you have to sweat. And he said, a genius is often simply a talented person who has done all his or her homework. So in other words, it all starts in the lab. You spend a lot of perspiration, a lot of hard work in the lab. And this is very important to understand. It doesn't, it's all start in a small lab, but you need some funding to do some research to really to come with these new ideas, new devices. But what is really challenging is how those ideas can really be applied. And as I said, not every device has made it to the market because it's challenging. And nowadays, actually, it's more challenging because cost is very, very important. You can have the best devices in the world, but unfortunately, if they are expensive, you cannot make money. So therefore, the transition from the lab to the fab is a big jump, and it takes time and efforts for these ideas to flourish. And I hope during this talk I'll just give you some few, an overview about how we can use the heterostructures to really make some devices which have got some special features, and they all use quantum mechanics. They are all quantum devices. And actually, if you think of it, practically every device we use nowadays, either electronics or optoelectronics, is actually based on a quantum phenomena. And this is why quantum mechanics play a big role nowadays in these new devices with the different properties, very different properties than classical mechanics. And thank you very much for your attention. I'm happy to answer any question you might have. Can you hear me?
Thank you very much, Professor Henini, for very interesting seminar. The topic is open for discussion. You get questions if you have related these topics. Please ask.
Now, let me just see how can I go back to the, because I can, shall I still share, or I'm not sure, because, so how can I go to the, so I'm not sure how to go back to my own, shall I just stop sharing? No.
Just stop sharing or something.
Stop share, yes. Okay, now I can see, yes, stop share, yeah, great.
So now the time for the questions. So I have one question. So what is the future of this quantum computer and this quantum field? So,
yeah. Well, quantum computing is something completely different, and it's still at the research stage. You say so. The quantum computing, there are different, routes where people are using quantum, practically some quantum dots devices, where they can access, these quantum dots. The problem with quantum dots, usually they're self-assembled quantum dots. These are practically nanoparticulates made, for example, indium arsenide, gallium arsenide. But the problem, they're not very aligned, but there are now some tricks which can align them both vertically and vertically. These are practically quantum boxes. But up to now, it has been very difficult to we can make these quantum boxes for lasers, quantum dot lasers, but they're not ordered. They're everywhere, but we don't care when you make lasers. But when you want to make a quantum computer based on quantum dots, you want them to be really, where they are. So you have to have some very good alignment, both laterally and vertically, in order to access each quantum dots. But of course, for the quantum computing, one of the biggest challenges of these devices is sometimes they don't work at ambient temperatures. You have to cool them to see this effect. All the devices I showed you today, they work at room temperature. That's what, and these lasers, which are quantum devices, they can even work at very high temperature. But some of these devices, they lose their properties or their quantum properties at high temperatures. So the biggest challenge is you have to cool them. And this is not a reliable way, to make some devices really, especially if you want to use it in your laptop. You don't want to cool your laptop to a certain temperature. If it was Peltier cooling or something, probably. But as you can see, some of these quantum companies, they're still at the early stage, and there are a lot of research. I talked up, for example, about single electron transistors. We can make a single electron transistor, and transistor which rely only on single electron, but it only work at liquid helium temperatures. Okay, when you warm it up a little bit, that's it, it doesn't work. So there is some issues about quantum computing to make it really work at ambient temperatures, even higher.
All right. Thank you very much. And any other questions?
Yes, Professor Henini, now you have mentioned that those quantum cascade lasers, they are mainly working in the infrared region. Is there any reason that cannot be developed for the visible region or coming to the UV region?
No, you see, with the quantum cascade laser, because that's what designed for. Because the problem to make a long wavelength, lasers, that means there's not many materials. System will give you that energy gap to be small. So you see, because you want to control that energy. Because if you look at normal laser, okay, it's just an electron from the conduction bond to an electron in the valence bond. So the energy of that photon is practically the energy of the bond gap. So usually, I mean, it's very hard to find a semiconductor with very narrow bond gap. That means a narrow, small energy gap to give you that long wavelength photon. It's very, very, very hard, you see. So that's why, using quantum wells, because now with quantum well, you can practically tune that energy as you wish. It doesn't depend on the material system. For the visible light, the UV light, you rely practically on the bond gap. The higher the bond gap of the material, the higher the energy, the shorter the wavelength, you say. But for the longer wavelength, it's very difficult to find a material system which can really tune that energy. You see, here I'm talking about few micron, 5 micron wavelength, 10 micron wavelength, 15 micron wavelength. So with this, you can do it actually just with the confined energy state in the quantum cascade lasers. You can tune that to any energy you like. Smaller to very larger, but it's limited, of course. So those are the trick. You see, for the quantum cascade laser, it doesn't depend on the material system. It depends only on the confinement. For the other lasers, it does depend on the bond gap. So that's very, very important. So use the bond gap for the generation of the photon.
Thank you very much.
Yeah.
Any other questions? In the message box, we have given a link to give your feedback. Please fill the feedback form also. Right? Any more questions? Please. Right. If no more question, I would like to invite our Joint Secretary of IPSL, Dr. Vasanthi De Silva, for a vote of thanks to Professor Henini. And over to Dr. Vasanthi.
Thank you, sir. So first I would like to thank our guest speaker, Professor Mohemad Henini, for your interesting and impressive webinar on modern application of physics from research to industry. So in your talk, you revised us the history of highlighted inventions via fundamental physics concept. It was very interesting to understand how quantum mechanics contributes to technological development. So this is a good motivation us to think different way about physics concept. So thank you very much. So once again, I would like to thank Professor Henini and also our committee members organizing this monthly webinar. So dear participant, thank you very much for your cooperation to success this event. So have a safe time, everyone.
Thank you very much. Thank you very much indeed, and I wish you a very nice day. Well, nice afternoon. It's it's afternoon for us too as well. So I wish you be safe and be healthy, and I hope to see you soon. I did visit, of course, the Colombo. Actually, the last time I was abroad, it was in Sri Lanka. Because I was on a holiday in Sri Lanka. That was 2019, September 2019, and since then everything has been locked down. So I hope we can meet sometimes in the near future.
Yeah.
I wish you a nice day.
Okay.
You
Thank you
too.
very much, sir.
Bye-bye. Bye-bye, everyone. Bye-bye. Bye-bye. Bye-bye.
So with that, we conclude, and we'll meet at the same time in next month. Thank you very much.